Hello and welcome to another episode of Invalid Entry. My name is James Taylor and today we're going to be looking at spirographs, specifically over-engineering the project scribbler to draw spirographs. So first of all, we're going to have a quick look at what spirographs are. There's a collection of these circular-based automated drawing going back to the Victorian era where they had a swinging arm with a table moving and a rotating table underneath. And I hope to build some of these actually because they're a lot of fun to get the output from. So basically a spirograph was a big thing, I think from the 70s, maybe the 80s. Still very big today. And actually there's more modern versions which are quite interesting. But basically what you have is you have a cog, a geared surface as an inner ring there. And then basically you have another cog on the inside with little dots on, usually in a bit of a spiral like that to give them space. And the idea is this has a cog, these teeth intermesh with that. So what you do is you put your pen in the hole and you put a little bit of force on to turn it. So this means this turns this direction, so it sort of goes around there. And as it goes round, the teeth mesh with those teeth and it progresses along the inside of this circle. Your pen then goes sort of inwards and outwards and actually traces a line around the circle. What you find is that the numbers are being quite carefully calculated so as not to be harmonics of each other. If you had a circle, an inner circle which had exactly half the number of teeth, 2-to-1 ratio, then what you'd find you'd be at, like, if you started at the minimum point there, you'd then be at the minimum point here, and then sort of maximum there, you just get a diamond come out. You want it to be slightly off, so you get these repeating patterns, so it goes over and over several times until it repeats itself. So that's a spirograph, that's your mechanical spirograph. When we're thinking about simulating this into Python, what we can actually do is imagine, instead of having an outer circle and trying to do the calculations of this inner cog, we can actually pretend that there is a circle which is a slightly smaller diameter, and this circle is actually moving its center point along that inner circle. And that just makes the maths a lot easier. Otherwise you have to work out sort of diameter out and then sort of the gearing. And the second thing we can do is we don't have to actually be bound by this gear ratio. We don't actually imagine there are teeth. We don't actually work out, well, if I rotate this way, it rotates a fraction along. We can actually do whatever we like. And the second thing is we're also not bound by the mechanics of you can only go this way. We can actually have this cog rotate backwards as it goes round this circle. So we can do a lot of things. For the maths, to work out the coordinates of this point over time, it's relatively simple if we think our origin is in the middle. So the first point is I'm going to pretend my origin is here, which when we talk about the scribbler and computer graphics, the origin is always actually at the top left, somewhere up here. But all we can do is we can just offset the XY point. So I'm going to pretend my origin is here for the math and then just add an offset of X and offset of Y to shift the spirograph around. Important concepts are that we have a radius, and I'm also going to be doing my maths in radians. A lot of people, a very, very brief, complete side channel, a lot of people like degrees. When you have a circle and you have an angle or a bit of a pie taken out, let's say that's the angle there, that's usually in degrees, i.e. something out of 360. The total amount is 360. And 360 degrees makes a lot of sense to humans because it's what we call a highly divisible number, or what some of us call antiprimes. It divides nicely. You can divide that by 2, you can divide it by 3, you can divide it by 4, you can divide it by 5, 6, 7. So I'm not sure about 7, but it divides evenly into whole numbers for loads of numbers. That's why we have 12 hours in a day, because it divides nicely into halves, thirds, quarters, and so on. However, it's not necessarily nice when you're doing your maths. When you're actually trying to do maths other than straight dividing, it doesn't necessarily make sense. So mathematicians often use something called radians. And when I was at school, I feel it was badly explained to me what radians were. So those 2 pi radians in a circle, which is completely opposite of this. That 2 pi doesn't divide nicely at all. You can't, well, apart from in half when you get 1 pi, but it doesn't give you nice whole numbers ever. And I think that's a bad explanation. And it's, instead of thinking about the degree, when you're dealing with radians, what you should actually think about is the distance travelled around the circumference. Because we know in a full circle there is 2 pi r circumference. So really, if there was a unit, 1 unit distance radius, then the distance travelled is always 2 pi for a whole circle. So if you have, say, I've gone 3 radians, you basically say I'm going 3 of that in total surface, and it's sort of, you see what I mean, it's the distance travelled rather than thinking about it's actually the angle. And when I realised that, I only realised this relatively recently. This was only explained to me this way. It makes sense as to why there's 2 pi radians, and actually it also then makes sense why a lot of the maths is easier. Anyway, we're always going to be measuring radians, and we're also always going to be measuring from this line here. So to get an angle over here, we're just going to be measuring all the way around counterclockwise. That may not be obvious. Counterclockwise to the top. Maybe it's clockwise. It doesn't actually matter. The maths will work itself out. Because we're going all around the circle, it doesn't actually matter. Anyway, to work out this point here, we've got to work out 2 components. We've got to work out the distance this way and then the distance this way. This is now a right angled triangle. Even when it's backwards, even when it's over here, it's still a right angled triangle, because you're still working out the y component and the x component, although this will now be a negative. Oh, sorry, I've just gone deep here. This will now be a negative value. This will now be a positive, but it's still a right angled triangle, which means we can use the sine and cos rule really nicely. So the distance across and the distance up. Sine theta equals opposite over the hypotenuse. Okay, in this world, because this is our theta argument, this is the op. This is the hypotenuse, and this is the adjacent. So opposite is the opposite angle, the line opposite to your angle, for those of you who never did this maths. Adjacent is the adjacent to the angle, makes sense, and the hypotenuse is the other one. It's the one, I don't want to say opposite this right angle, but it's opposite the right angle. We don't have to use the word opposite because opposite over here. So you've got an angle which isn't the right angle, opposite is there, adjacent is there, and the hypotenuse is the other one. That's how I remember it. It's Greek, I think, and not for hippos. I like hippos, but it's not for hippos. Anyway, so the sin of that, rearranging that, because I know the hypotenuse, which is the radius, so we can now just rewrite this as times both sides by the radius, kills that, times hype. So radius sin theta times sin theta equals what would be the y axis. The cos rule is cos theta equals adjacent over hype, where the adjacent is the x-axis. So the radius times cos theta equals the x value, and that is the 2 formulas that we're going to need. Now, when we've got another circle, again, we can pretend that we've got another circle here with a separate angle on it, a different angle, whatever we want to use it, and then we just add the y components together and the x components together to give us that offset. What we then do is remember that point, we then adjust the 2 angles very, very slightly, and because we're working in radians, we're going to adjust them probably by about 0.1. Remember, the entire circle is only 2 pi, 2 times 3.14, so it's about 6.3, right, roughly. So you'll want to move by about 0.1 to get these little steps, and then we'll see what it comes out with. So I'm going to swap to Python now, and we're going to code this up super fast, and I'm going to demonstrate just a couple of functions I have locally. Okay, so as I briefly mentioned on one of my previous videos, I've started building out these libraries of functions, which will basically build up to being a collection of toolkits or tool chains to run the Spirograph, or to run the Project Scribbler machine. So what I've got is a prototype function which actually draws what it's going to look like, so I don't have to actually run the machine. I can actually make sure it's going to fit on the machine and everything before I do it. It also draws the arc of the current length from the rest point, so I know that's the rest point. Very vaguely speaking, I think I talked about it before, anything above this line, the tension becomes too hard, it begins to skip steps. Anything outside this line, it doesn't really render very nicely or very neatly, so I want to get my picture really inside. I've also got 2 other handy path functions here. I've got a scale function and a shift function. I'll demonstrate this very quickly. So here's a coordinate being rendered, so that is a path there. If I want to shift that, equals shift chord paths. I then pass in an argument of, let's say I want to shift it by 100, 400, so it's going to shift along by a little bit and down by 400, and there you see it's been shifted out there. If I want to scale it, I can do the same thing. I can scale it by 2, which means that it's now twice as long out there, or I can scale it by 0.5, 0.5 like that. and it becomes half as long. So I can now sort of scale and position these things nicely. And I can daisy chain these together a little bit, so I could then do, I can now say I want to shift. I can scale then shift, and I can shift and scale. There is a loss of accuracy or precision every time we do these functions, because if there's floating points there, they will adapt. 200, 200, like that. I can now shift that scaled thing down there. So, what I want to do eventually is actually have a GUI so I can click buttons and then scale it and stuff, and it will just click and move to where I want it to be. But that's fundamentally, I've got these functions here just to help. And that's going to be helpful because I'm going to be calculating my spirograph from 0, but then I'm going to want to shift it right into the middle of where I'm going. I think I talked about this briefly as well. My coordinates are actually an array of arrays, so I can put 2 arrays in here. And let's put these over 400, 200, 200, 200, right, like that. And you see I've actually got 2. Now the green line here is the pen up movement, so it goes white, green, white, because it's going to go pen up and then down. I have got some other functions which optimize the pen up movements and things like that. I'm not using those right now. At the moment, this is just to demonstrate that. For spirographs, it's all going to be done in one seamless movement, so it's going to be one seamless movement in the middle. So let's crack on. I'm going to need to import maths, by the way, because we're going to do maths for the sin and cos operations. So very basically, the idea is that I have 2 angles, both at sort, and I've got 2 radius. And my radius is the scale here is one pixel is 1 millimeter here. So this is the entire width of my machine. About 975, I think it is. I've got it written at the top. 950 at the moment. 950 millimeters. So this is all calculated on that. So my radius 1 is going to be about 500, and my radius 2 is going to be about 200. Now, the maximum it can go is the 500 plus the 200, because the maximum extension is it actually is extended out, like it's on maximum one and maximum of the other. So just be aware of that, and then my renderer will show if it's bad or not. So for I in range, I don't know, let's do 500 points. I could build a bit of logic to actually detect when it's gone round, but it is. And the other thing I'm going to import very randomly here is yeah, I'm going to import random, and I'll explain why I import random. Just because it really annoys me that math actually has pi, but it's spelled differently in capitalization to random, and I actually want 2 pi anyway. Anyway, so for anyway, so what we're going to do now is go angle 1 plus equals step 1 equals 0.1 and step 2 equals 0.01, 0.7, because I don't want them to be harmonics of each other. So angle 1, they think about the number t. So angle 1 plus equals step 1, angle 2 plus equals step 2. Now the x is going to equal the as we said a moment ago. I've got a bit of paper, so I put down a moment. My x step is actually going to equal radius 1 times math.cos angle 1. Okay, nice and easy. And then plus radius 2 times math.cos angle 2, like that. Nice and easy. And then the y is going to be math.sin and math.sin. Okay, a couple of things I want to do is here say if angle 1 is greater than random.2 pi angle, or rather while, because just in case these are stupid, someone put stupid numbers in here, angle 1 minus equals random.2 pi. Basically, once you go around the circle, I subtract entire circles until it ends up back in the original circle, only when it's bigger. And then I'm going to copy that again for angle 2. There we go. We're going to define chord paths equals an empty array, and path equals an empty array. At this point, we're going to do path.append that x, y coordinate. Nice and easy. And here we're going to chord paths.append path, because I always have to have that double away, even though I only got one entry. Do it like that. Let's see what it looks like. Now, very, very big, centered in the middle. My numbers may be a bit big. Let's reduce these down to 300 and 100. There we go. Absolutely horrendous. As I said, though, we want to offset that, and we want it to be in the middle. So my current width is 950, so I'm just going to do 950 divided by 2. Chord paths equals chord paths dot shift. No, sorry. I think I called it shift, yeah. Shift chord paths. I'm going to turn this into an object, so you actually do object.shift, object.scale without actually affecting the underlying object, but I haven't done my OO programming yet. But that's a future video, and let's talk through the architecture of that OO programming this. So shift this by 950 divided by 2 and 650 divided by 2. And I'll just go hard that one there, so I don't want to introduce more flow together. Still a bit big. Let's just make this 100, 200, 175. Okay, so this is the beginning of spirographs, and what we're going to do now is we can just play with these numbers here. 0.1 seems to be right there. Play these numbers here to get the spirograph coming out. And that is a spirograph. That is your most basic spirograph written in the most inelegant way whatsoever. What we can now do is actually run that on the machine. So the way I'm going to run that on the machine actually is really simple. I'm going to import JSON first of all. With open, I'm just going to check my code because I actually have done this right. There we go. With open spiro.json with write mode as fp, json.dump, not dumps but dump, chord paths fp. And I will do this completely live, so that will now save that spirograph into the into my spiro.json file. Okay, so we've swapped to the spirograph visualization mode. I had to just adapt the code very slightly because I was actually using a very slightly different version, which was doing the scaling actually at the point of time of drawing. And since I've got this tool chain now, I don't need to. So you see, actually I was wrong. It is going clockwise. I don't know why I thought it would go counterclockwise. We're going clockwise. It's a series of little steps that I brought in here. This actually isn't helping. The pen up, pen down. I'm actually thinking about adapting the pen up, pen down to be battery powered on a Bluetooth, which means I can actually not have this third wire to do the pen up, pen down. But we can see here we're getting roughly what I wanted from the input. There is still a little bit of inaccuracy here, and I am a little bit worried about my scaling factors. I think sometimes stop it having circles or the up-down scaling doesn't seem to be working out quite right. But generally speaking, this is now, again, this wire here is just being awkward. The angle of the body is tilting away slightly, so you can sort of see it sort of gets dragged across, and as it gets dragged, that angle is causing these deformities to happen here and here, which is a problem with the gondola design. But because I'm using a whiteboard, anything which actually sucks itself to the board just rubs off the picture. So there is a bit of a give and take there. If I use like a Sharpie on paper, the ink dries fast enough that I don't need to worry about that, and I can actually have the thing flush against the paper. So at this point it's basically going over the line it previously had, which means I'm already back on that harmonic, which means we can stop the program because this is basically done. So the number of steps, I actually put in the program, I could put some optimization saying if you're going over lines you've already drawn, you don't need to. But yeah, that's basically this spirograph drawn. So lots of deformities at the scale. It isn't quite what we want, but the point is it works in premise, so we can sort of move on. Moving back on then to this, this is a bit ugly, and actually the spirograph, again, we can actually do some really cool things where instead of just having 2 circles, we can have more circles. So if I add another circle in, it will be step 3, and this gets longer and longer. So instead of this, what I'm going to do is actually think about this thing of circles. And a circle is going to be an array, and they can be big, small, little, whatever, I don't know. But each circle is going to have a size. So each circle is going to be a dictionary. It's going to have a size, which is going to be 100, or so it's going to have a radius. And it's going to have an angle, which at this point is going to be 0. And it's also going to have a step, which is going to be 0.1. And we can define that now as 2 things. So the next one was going to be 75, and a 0 step point 0.06, like that. Okay, so we now have an array of these things. So I can get rid of all these things. Here, I can basically say x equals 0, y equals 0, and I'm going to use those in a second. So the reason I reset that on every point is important. Okay, let's say for circle in circles, circle angle plus equals circle step. Like that, very simple. And then I'm going to copy this bit here and basically say while circle angle is greater than 2 pi, circle angle minus 2 pi. Nice and easy, job done. And then I can now take this component here, these 2 components, and instead of making them equal, make them plus equals. So they're now going to be appended to. So it starts at a non, resets that every time, and this is going to be circle angle. Every time I've got that, it's going to be circle angle. Boom, 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 boom. Again, nice and easy. Get rid of that. And then that happens X times. So it's going to append on the first one, the second, and so on. So this here, this refactor here, at the moment that was the old picture, run it again, gives us a bigger picture. And why did it give us a bigger picture? Because here I didn't reset my radius. So my circle radius here should be circle radius, like that. Basically I just used what was previously in scope, that radius 1 twice. And that should give us the smaller picture. It's actually still going to be a very big picture at this point. That all looks right. Did I have my previous one wrong? What was my previous code? Oh, no. Hold on. I don't need the second component. Give me that. Sorry, I don't need that. So this here should be circle radius, as should that. So this because I'm running around this loop twice, it appends the first array, then it appends the second array, so on. So that's the same as the first picture. But what we now have is the ability to actually do 2 circles inside the first one. So this one's going to be 25. Now it kind of makes sense that the circles get smaller. They don't have to. If they don't get smaller, you have weirder effects going on. But they can. And it also makes sense that the step size is actually bigger. 1, 2, like that. And you start getting different patterns. Obviously this one isn't circular, you start getting these different patterns of spirographs. If they aren't harmonics of each other, you get more wacky things come out. So the less harmonious, the more chaotic the output. 1, 5, 0, 4, 3, 2, 1, like that. Okay, so you start getting these they're not very spirography. So if you do make them harmonics of each other, if they're 2 harmonics, so 0.1, 0.05, and 1.15, for example, we'll come up with something that isn't very chaotic at all. And you see here it's actually gone on the line several times. The thickness is because it's not quite exactly the same points each time around. So you kind of want to think through these things as being but the thing is, now we now have a scalable solution, a scalable spirograph, which is the most again, I'm halving this. Well, I'm not really halving it. It's 50 there. 50. The most. And I can also make one negative. So So that means one of those circles go around backwards, and you just start playing with these numbers. So what we now have is the most over-engineered spirograph ever, and every single one of these is now runnable because I just say save it as the Spiro function, flip to my supercoms, and we're about the previous one really quickly. One of these is, there we go, found the right function. So yeah, basically this is the Spirograph thing done at this point. I can just sit back, hands up, go, I'm not controlling this anymore, not joysticking it. It is now the most over-engineered Spirograph in existence. I don't really know what else to add at this point. Have fun. Go invent, make stuff. It's very hard to sit here in silence and not try to pad with banter.